right. So welcome. Today we're going to start talking about the Laplace transform. So first, just sort of some initial definitions. So first, what sort of thing is the Laplace transform? Oops. So the Laplace transform takes a function f of t and spits out a function of s. It's most commonly denoted by sort of this notation. You got this fancy L, curly brackets f of t, and then just to emphasize that it's a function of s, we put an s there. So the other notation that we'll use sometimes is if we start with f of t, we'll often write capital F of s. Now it should be noted that this is more than just choosing a different variable. So the Laplace transform of t squared s, for instance, is not just s squared. In fact, it is 2 over s cubed. So we'll look into some more examples. But of course, a question I'm sure you're asking is, well, why do we care? Why are we introducing this? Well, one of the reasons, and sort of the main reason the main thing we're gonna use it for is it turns differentiation into multiplication by s. And there's sort of a star there. That's not quite true. We'll see what the actual formula is eventually. So it sort of lets us turn an ODE into just algebra. And so we can sort of solve the algebra, and that's going to actually end up solving the ODE. Okay. So enough build-up, let's just get into the definition. So the Laplace transform, or sometimes called the one-sided Laplace transform, of a function of t is defined by the following integral. So it's the integral from 0 to infinity of f of t times e to the negative st dt. And remember what this notation means, 0 to infinity. That's the same thing as, let's say, the limit as capital T goes to infinity from 0 to capital T of f of t e to the negative st dt. All right. So let's look at our first example. Let's compute the Laplace transform of 1. Okay. You can also note, sort of omit the s, but just like, no, it should be there, sort of just secretly. So Laplace transform of 1, right, is the integral from 0 to infinity of 1 times e to the negative st dt. All right, so now we just want to sort of take the integral of e to the negative st. This is a pretty straightforward u sub, right? U equals negative st, so du equals negative s dt, and dt equals du over negative s. I'm not going to sort of worry about the bounds now, but this is just e to the u. And so we get that the Laplace transform of 1 is the limit as capital T goes to infinity of e to the u, which is e to the negative st, over negative s from t equals 0 to t equals capital T. E to the 0 is 1 over negative s. And so now we want to sort of see what happens to this. So this 1 over negative s, there's no t's there, so we can just sort of ignore that. So we get that the answer is the limit as t goes to infinity of e to the negative st over negative s, and then that's just plus 1 over s. Well, what happens to this integral? Well, if the top part here, if this negative s is negative, or rather if s is positive, then what we end up with here, right, is that this goes to 0. Right, so if this is positive, then this is going to be greater than, or less than 1, rather, and this is going to go to 0. On the other hand, if s is less than 0, so like if s was negative 1, then we would just be taking the limit as t goes to infinity of e to the t, and that's going to go to infinity. The last case is if s equals 0, then note our steps back here are actually invalid. So this is not the integral if s is 0. if we go back to here, we see that if s is 0, this is just going to be the integral from 0 to infinity of 1 dt, which of course is also infinity. So what we have is sort of the following cases. So L of s, or the Laplace transform of 1, is equal to 1 over s if s is greater than 0. And it blows up sort of equal to, I guess, infinity or negative infinity if s is less than 0. Less than or equal to 0. Yeah, so this would be our final answer. And usually the way we represent this is, we know sort of implicitly that it's going to blow up in some cases, but what we say is just when is it not going to blow up. So we'd say the Laplace transform of 1 is equal to 1 over s for s greater than 0. Okay. So let's look at another pretty simple example. So let's look at what happens if we plug in an exponential function. So let's look at e to the 3 times t. So integral from 0 to infinity of e to the 3t times e to the negative st dt. Okay, so this is going to be, note that is an s, not a 5, but we can combine that together. So e to the 3 minus s t dt. And now this is pretty straightforward, right? The antiderivative of that, we're going to have the limit as capital T goes to infinity of e to the 3 minus s over 3 minus s from little t goes to from 0 to big T. So we get this. Again, we sort of want, for this to converge as t goes to infinity, we need 3 minus s to be less than 0. Again, these steps aren't right if s is equal to exactly 3, but it would still blow up in that case. And if this is less than 0, then the limit as t goes to infinity of e to the 3 minus s times t over 3 minus s just equals 0. And so our answer is just going to be 1 over 3 minus s, or we can rewrite that as s minus 3. So our answer for the Laplace transform of e to the 3t is equal to 1 over s minus 3. And we need 3 minus s to be less than 0, which is the same thing as s being greater than 3. So this was pretty straightforward. Let's see if we can come up with sort of a general formula. So can we compute the Laplace transform of just e times a to the t, or e raised to the a times t power? Okay, so if we have this, we sort of know what's going to happen, right? We're going to end up with the same thing. Limit from capital T goes to infinity of e to the a minus s times t over a minus s. And the same sort of steps are going to follow from up here, right? We would need this exponent to be negative, otherwise it's going to go to infinity. So what we're going to say is just we need a minus s to be greater than 0, or a greater than 0. I'm sorry, a greater than, sorry, I have that backwards. We need a minus s to be less than 0, which means that a is less than s. And if we do, then what we'll get is just 1 over s minus a. So our answer is the Laplace transform of e to the at equals 1 over s minus a, and this is sort of only valid for s when s is greater than a. So this is sort of a nice general formula. So let's look at another example. So let's say using our formula, that we got from the previous problem for the Laplace transform of e to the at, let's compute this. So we're going to sort of take a shortcut here, but this is actually what we're going to do a lot of the time once we sort of get comfortable with computing these using the definition. So, okay, so by definition, right, I have the Laplace transform of 3 e to the t minus 6 e to the negative 7t. And remember, I can distribute, and also I can split up integrals. I guess I should be indicating the bounds here. Minus 6. All right, and then if I look at this and this, I see that this integral is now the Laplace transform of e to the t. And this integral is the Laplace transform of e to the negative 7t. And so if I use these formulas up here, so this is going to be 1 over s minus 1, and this is equal to 1 over s minus negative 7. Should be noted this is valid for s greater than 1, and this is valid for s greater than negative 7. So then what I get is 3 times 1 over s minus 1 minus 6 times 1 over s plus 7. And I need both of these things to be true. Well, if s is greater than 1, it's definitely greater than negative 7. So we get our final answer is this, and it's valid for s greater than or equal to 1. All right. So, oh, actually, sorry, before I get into the exercise, so a property of Laplace transform, really the linearity property, so if I know the Laplace transforms of two things, and I look at, so if a and b are coefficients, then I can compute the Laplace transforms of f and of g, and then just combine those to get the Laplace transform for the sum. And, you know, why is this true? Well, because I can always split apart an integral, right, like this. So this thing, right, is the Laplace transform of a times f of t plus b times g of t. And we see down here, well, this is a times the Laplace transform of f of t plus b times the Laplace transform of g of t. All right. Okay, so there's going to be two exercises. First one's going to have 2 parts. So for problem 1, so using the definition. So this means for one of these we're going to have a formula. Don't use it. Try to do it directly. So using the definition for the Laplace transform, compute e to the negative 7t, Laplace transform of that, and the Laplace transform of t. For this one, you're going to need to do integration by parts, but it's pretty straightforward. And then for part 2, use your answer from 1b to compute the Laplace transform of e to the 6t plus 5 times t. Right. So give those a shot, and make sure on all of them to also indicate for what s values it's valid. All right. So again, this one actually, do the integral, but you should have gotten, as we sort of already know, that your answer should have been 1 over s plus 7, and it was valid for any s greater than negative 7. For this one, I'll say a little bit more about. So what you should have gotten for your antiderivative of t e to the negative s t dt was t e to the negative st over negative s plus 1 over s, the integration by parts, e to the negative st over negative s. And so your answer would then be negative t e to the negative s t over s minus e to the negative st over s squared, evaluated from 0 to infinity. And if you did that, you would have gotten your final answer. So integration by parts there would be 1 over s squared, and it's valid precisely when s is greater than or equal to 0. Okay, so for this one, for your answer, right, this is the same thing by linearity of the Laplace transform of e to the 6t plus 5 times the Laplace transform of t. So this we had a formula for. It would be 1 over s minus 6. We need s to be greater than 6 there. And this should be 5 times 1 over s squared. And we need that to have s greater than or equal to 0. So what we get is, well, when s is greater than 6, it's automatically greater than 0. So our answer would be this when s is greater than 6, or for s greater than 6. All right, that's going to end this one.